Okay, good evening. This is our 11th lecture, and we have discussed about the different possible phase orientations within between the two phases. If we have vertical and horizontal pipelines, and then we also try to solve that if we have some phase change heat transfer cases, then how the flow designs will evolve. Okay. Now, what we will try to do now, we will try to focus on the shapes of individual particles present in the flow field. Okay. So, particles, as I told you earlier as well, that we will be having two types of particles, solid particles and fluid particles. So, solid particles are of rigid nature, and then fluid particles are having actually flexibility in terms of changing its shape depending upon the surrounding flow field. Okay, so we'll try to see what are the different shapes possible for particles and how these shapes actually can be characterized, because later on whenever we will be doing the subsequent interaction of the particles with the surrounding fluid, then the different interaction forces will depend upon the shape of the particles. Okay, so whenever we talk about the shape of the particle, so first of all we will quickly try to see the shape of the solid particles. Of course, whatever this classification I am doing, this is applicable even for fluid particles as well, but what I want to convey is that in case of solid particles, actually we will be having the infinite number of possibilities. Okay, because the shape of the solid particles can be of any arbitrary type. Okay, on contrary, whenever we will be talking about the shapes of the fluid particles, then of course fluid particles will also be having the multiple different types of shapes, but the nature of a particular shape will be actually depending upon the dynamics of the surrounding fluid as well. Okay, because ultimately whatever the shape for fluid particles we see, that is nothing but the static equilibrium in between the normal and the tangential forces at the interface. Okay, so whereas all the forces, normal as well as tangential, are actually coming in equilibrium, so that type of shape a system, a fluid particle will actually acquire. Okay, so that's why for fluid particles we will be having slightly finite number of the shapes. So first, if we see the classification of particle shapes, then we can classify the particle shapes based on the symmetry. So based on the symmetry, the very first type of particle we can call as nothing but the axisymmetric particles. Okay, so in case of axisymmetric particles, what typically we have some axis of symmetry, and about this axis of symmetry, if I have any closed curve, if I simply rotate this closed curve through 360 degrees, then what I will be getting? I will be getting one axisymmetric particle. Okay, if my curve of symmetry is nothing but a circle, then I will be getting a spherical particle. If this shape is other than the circle, then typically if shape is close to ellipse, then we call the particles either as spheroidal particles or ellipsoid of revolution. Okay, so now one interesting factor comes, with the help of which actually we can characterize further the axisymmetric shape of the particle, and that particular factor is nothing but aspect ratio. Okay, so if you have a particle, so of course particle will be having some projected length and some projected width. Okay, so if we consider that the ratio of length projected on axis of symmetry to the maximum diameter normal to axis. So it means what it is talking about, it is saying the ratio of B by L. Okay, so if you have say this type of particle which is having dimension, this dimension as B and this dimension as L. So typically the axis of symmetry will be here. So which length is projected on axis? The length projected on axis is B. Okay, and the other length which is normal to the axis is nothing but L. So ratio of B by L we are calling as aspect ratio. So if this aspect ratio is less than 1, it means value of B is smaller than L, then I will be calling my particle as oblate spheroid. On contrary, when E is greater than 1, then we will be calling it as a prolate spheroid. So, in case of prolate, shape will be something like this, and this is my axis of symmetry. Okay. So, then my B will be greater in comparison to the L. Okay. Now, of course, from the shape itself, you can actually little bit some idea of fluid mechanics will be coming to your mind. If you have this type of shape and flow is happening like this, then this is from the fundamental fluid mechanics. It is acting like nothing but a bluff body. On contrary, if you have a prolate shape and flow is happening like this, then it will become like a streamline body. Okay, so if you try to relate from the fundamental fluid mechanics, so how shape is actually making an important role, because in case of this oblate shape, if flow is like this, then majority of the drag contribution will be coming from the form drag and skin friction drag will be actually less. On contrary, if your shape is like this, then form drag will be less and we will be having major contribution from the skin friction. Is this one clear? So then we can also define some particles as orthotropic particles. So if we have a particle which shows symmetry, plane of symmetry about 3 mutually perpendicular planes, then we will be calling that particle as orthotropic particle. Okay, so if you take a simple cylinder, rectangle, so all these will be about their mutually perpendicular planes. For example, if this is my one shape, and what I can do, I can take one plane like this, one plane like this, and third plane like this. So in other axis. So about all these 3 mutually perpendicular planes, once my shape is actually symmetric, then I will be calling it as a orthotropic shape. Okay. Now, one special type of particle we have, which is called as actually spherically isotropic particle. Okay. So if we have any particle, whenever this particle is actually freely falling in a uniform flow field, if particle remains in its vertical orientation and it does not undergo any type of rotation and its settling velocity is independent of its orientation, that particular type of particle is called as actually spherically isotropic particle. Is this one clear? Okay. So if you have, say, uniform flow field of the surrounding medium, and in that uniform flow field some particle is actually settling down. So once it is settling down, it does not undergo through any rotation. It means it is not changing its orientation while it is actually moving down. Okay. Yes, I have subsequent examples in the subsequent slide. Okay. So typically regular polyhedra and the shapes which are obtained symmetrically by symmetrical smoothing and cutting pieces from this type of regular polyhedra, these are called as actually, these comes under the category of spherically isotropic particles. And before going to all the examples in the next slide, we have to also see one more category which is called as isometric orthotropic particles. So any particle shape for which half body is obtained by cutting the particle along a plane of symmetry is same if I choose any plane. So it means that if I have a body, and in this body, when I am considering the plane of symmetry, if that plane of symmetry is dividing the body equally in 2 halves, okay, then I will be specifically calling it as isometric orthotropic particle. Okay. So for example, if you consider a cylinder, in case of cylinder, what will be happening? We will be having 3 planes of symmetry. One is like this, one is at the center, but they are not producing the 2 halves in the same orientation. On contrary, if you take a cube, in case of cube, if you take 3 perpendicular planes, then every time my half body shape will be actually identical in all the 3 planes. So that's why cube I can call as isometric orthotropic particle, but not a cylinder. Is this one clear? Okay. So now let us try to see some examples of these shapes. So if I have circular cylinder, circular disc, spheroids, then all these are nothing but axisymmetric. But these are not orthotropic. Because for orthotropic, if I take any random plane of symmetry, then it should divide the body into identical shapes and two parts. Okay. So that's why cube I am calling as nothing but a isotropic, this orthotropic particle. Okay. Now, if I talk about a cone, then cone is axisymmetric, but it is also not orthotropic, because, and overall if I see, none of all these shapes are actually spherically isotropic. Okay. On contrary, if you talk about parallelepipeds, then all these shapes are orthotropic, but cube is the only special type of this shape which will be actually spherically isotropic. Okay. And if I talk about regular octahedra, so this is octahedra given over here. So octahedra and tetrahedra are again spherically isotropic, but only octahedra is orthotropic wherever tetrahedra is not. Because octahedra in any three mutually perpendicular plane, if you cut it in about the plane of symmetry, it will be giving you two identical shapes in all the orientations. Okay. On contrary, for tetrahedra, if you cut, then it will not give you the identical, particularly in the third plane, which is parallel to the this base of the body. Okay. So these are some examples. What you can do, you can try applying these fundamental definitions to different bodies, and then you can try classification of these shapes further. Okay. Now, whenever we are having these shapes, we have classified the shapes, but classification does not solve our purpose. Okay. Ultimately, what we need to do, whatever these irregular shapes we are having present in the system, all these irregular shapes will be actually interacting with the surrounding liquid. Okay. So once these are interacting with the surrounding phase, whether liquid or gas, when these will be interacting with the surrounding phase, as I told you that we will be having some relation for drag force, some relation for lift force, etc. Okay, so which will be actually giving me the interaction forces. Now typically, if I have to theoretically derive these correlations, theoretically these relations are actually easily available for spherical shapes. Okay, but not for the irregular shapes. Okay, and even whenever you will try to do the theoretical analysis for simpler shapes which are say axisymmetric or orthotropic, for all these shapes from the theoretical equations you can easily identify the forces acting on the body because of the surrounding flow. Okay, but when you are having very arbitrary complex shapes, then you cannot calculate these forces. Okay, so that's why what we want to do, we want to specify some shape factors. With the help of these shape factors, if I know the relation of drag force or lift force for a spherical particle, same relation can be utilized for the other complex geometries by using some multiplication factors. Okay, so what are these multiplication factors or multipliers? These we are calling as nothing but the shape factors. Is this point clear? What is the need for studying shape factors? Because whenever you will be particularly talking about the flow of interaction of solid particles with the surrounding fluid. Okay, so in case of solid particle interactions with the surrounding fluid, you cannot determine all the forces theoretically for any arbitrary complex shape. Okay, so what you need to do, you need to determine the correlations for simplified geometries, relations for simplified geometries from the theoretical analysis, and then you will be using some sort of multiplier factors in order to multiply these factors for complex shapes so that their drag force or lift force or other hydrodynamic forces can be related to the equivalent spherical particles. Is this point clear? So when we will be making this equivalence, what we need to do, we need to first know some primary fundamental parameters of the particle. So for example, one parameter of particle is volume of the particle V. Second can be surface area of the particle A. Third can be projected area of the particle AP, and fourth can be projected perimeter PP. So these four, we can take the fundamental variables, and if we know these fundamental variables, then how with the help of these variables actually we can try making the equivalence of a non-spherical particle to a spherical particle, that we will actually try to see. Okay. So here what we have is, first factor I am calling it as a volumetric safe factor. Volumetric safe factor is given by symbol K, and it is nothing but equal to volume of the particle divided by dA cube. What is this dA? If you see the definition of dA, it is nothing but square root of 4AP by pi. So it means AP is nothing but projected area. Okay. So projected area will be pi by 4 dA square. So dA is nothing but square root of 4AP by pi. Okay. So what I am saying is, volumetric safe factor is nothing but a quantity which is equal to exact volume of the particle divided by cube of the dimension, which is equal to 4AP by pi. It means I can call this dimension dA as nothing but the projected area equivalent sphere, diameter of projected area equivalent sphere. Is this one clear? What is dA? dA is nothing but projected area equivalent dimension. Is this one clear? So it means that if you take any particle, if you take the projection of the particle, if you take a sphere, what will be the projection of the sphere? Circle. You will be having a circle, and what will be the cross-sectional area of this circle? Of course, this whatever the cross-sectional area of the circle, same will be the projected area of the circle. With reference to this projected area, whatever diameter you will be getting, that will be nothing but equal to the diameter of the sphere. So if you consider that volume of a exact sphere divided by dA cube, that will be actually coming out as factor K. So it means factor K will be nothing but, what is the volume of the sphere? 4 by 3 pi r cube, or in terms of diameter it will become 1 by 6 pi d cube. So it means that if you consider a sphere, for a sphere value of K will be equal to pi by 6. Is this one clear? All are clear with this idea? Yes.
Sir, projected area to different orientation.
Yes, projected area will be different in different orientation. So that's why typically what happens, whenever I am considering the particle under consideration, then we will try to see the direction in which actually particle is facing the flow. In that particular direction actually we will try to take the projection of the particle. Okay. So the way you do in case of your fundamental fluid mechanics. So when you are having fundamental fluid mechanics, one simple formula of drag, half CD into rho V square multiplied by projected area. So for cylinder, projected area is something different, for sphere projected area is something different, for a streamline body projected area is something different. So in different directions we take actually the projections. So that will be the subsequent complexity. Whenever we will be talking about the flow, there we will try to see that. Once we will study the interaction of these particles with the flow. So at the moment I am just trying to give you the possibilities, what are the generic possibilities with the help of which we can actually characterize safe factors. Okay. So volumetric safe factor is clear. What we need to do is, if I have to calculate volumetric safe factor, I must know the volume of the particle, and then I should do its projection calculate projected area, and then using this relation I should calculate dA, and then I can actually find out this. Now this is having so many complexities if we go into the practical considerations. Okay, so in the practical consideration, you will not be able to calculate the volume of the particle. So volume of the particle will not be known to you. Okay, and because of this, what we need to do is, let me show you in the next step. So first, let me tell you the methods to calculate AP, how we can calculate AP. Okay, so say you have a photograph of the projected area of the particle. So any random photograph you have, this is the projected area of the particle, AP. Now you need to calculate how to calculate this AP. So what you can do, you can take this grid structure something like this. So this is a transparent paper, and you can place this transparent paper on this, and then by counting the number of grids and their approximations, actually you can calculate the approximate value of the projected area. So this will be a rough estimate of calculation of the projected area. So whatever the value you will be obtaining from this method, that will not be very correct. So there is another improved approach which is proposed. So in case of first improved approach, what is shown, you have to take two images of the particle projected area, and you have to superimpose both the images one over another, and then you have to start displacing one image such that it is just reaching to the, it is making just a line contact with the outer boundary of the other particle. Okay, so like this. So first both these shapes were superimposed over each other, and then I slowly started moving this. Okay, and I have moved this image till the point it is actually reaching here. So from this point to this point, how much this particle has been traveled, it is called as image shearing diameter. Okay, what we call this? Image shearing diameter. So this is a image shearing diameter in this particular direction. Now I can also move this image in the upward direction. I can also move in downward direction, rightward direction. I can move arbitrarily in any direction. Okay. So what I have to do, I have to do multiple trials in all the directions, and then determine different values of image shearing diameters. And if I simply take the mean of these image shearing diameters, that will also give some approximate value of degree. Is this one clear? So this is the second method. All are clear with this second method? Then we have third method. In case of third method, what will be happening? This particular projected area, we have to divide through a plane or through a line in such a way so that it is divided into two equal areas. So A1 is equal to A2. Okay, so this area I have drawn a line in such a way so that my projected area is actually bisecting. Okay, so once I have done bisection of the projected area, then I will be getting one diameter. Now this bisection I can do in some another orientation. That will be my second statistical intercept diameter. Then like this I will be doing a number of statistical intercept diameters, and if I take their average, that will be another estimate of. Okay, so this is how actually people have evolved in the history. So long back, say in 1890s or 1910, how people, what type of methods people were actually using. Okay, but still the major concern is that you will get some approximate of dA, but not for volume. Okay, so that's why there is another approach which we can employ for practical considerations. Okay, so for practical considerations, what we need to do, we need to define two ratios. One is called as flatness ratio, and second is called as elongation ratio. Okay, so any particle you are having, you have to first superimpose three mutually perpendicular planes on that particle. Okay, and whatever the plane which is countering with the smallest thickness portion of the particle, that will be my thickness plane. Normal to that thickness plane, whatever the other plane I am getting, that will be my B plane, and a plane which is normal to both of the earlier planes, that will be my L. Okay. Now if I take the ratio of B by T, that I call as flatness ratio. But when we have to start, you have to remember one thing, that our first plane for estimation of the thickness, whenever actually I am placing, I have to place in minimum thickness zone of the particle. Is this one clear? All are clear with this idea?
Sir, technically T and L, sir.
Yes. So what I am saying is, say you have a particle of any arbitrary shape. Okay. So you have considered one plane along the thickness direction of that particle, and you have placed that particle in that plane in such a way so that it is actually the boundary of the particle is actually crossing the minimum thickness portion at that intercept plane. Okay, and then another plane you have placed perpendicular to that. That will give you B. And when you placed the third plane which is perpendicular to both, that will give you L. Okay. So based on that, we can define flatness ratio, which is B by T, and elongation ratio, which is L by T. And then you can use a formula K, which is nothing but equal to Ke times. So K is some empirical factor. This is some empirical factor divided by E1 into square root of E2. Okay. Is this one clear? So by using these three, now E1 and E2 you can simply calculate for a particle. But if you have a particle of smaller size, what you need to do? You need to visualize the particle through, say, microscope. And there you have to take the projections and images of the particle in different orientations. Then you will be able to calculate T, L and B. And after that, you have to multiply with some empirical factor. You have to divide this E1 into square root of E2. Okay. So in this case, if you use this method, then what are the values of Ke for different shapes, that is given over here. So this is for regular shapes, for sphere, cube, tetrahedron, cylinder. These are the shapes. And then if you have isometric irregular shapes, then if you have, say, rounded shape, subangular shape, angular shape, then what are the different values of K? And then even depending upon the materials, for example, if you have a sand particle, bituminous coal particle, gypsum particle, then what are the different values of Ke? These are actually available to us from this particular table. Okay. So by using these tables and doing the basic length calculation of the particle, actually we can calculate the values of shape factor. And how shape factor will be useful? Whatever the relation of interaction forces are applicable for spherical particle, same relation can be applied for complex shapes, non-spherical particles, by just using the multiplication of the shape factor. Like multiplication or sum power. So that will be coming as a multiplier. Okay. So now another important factor is sphericity of the particle. It is given by a symbol psi, and it is nothing but equal to surface area of volume equivalent sphere divided by surface area of the actual particle. So what do you mean by volume equivalent sphere? Whatever the volume of the particle is there, if I write this volume in terms of equivalent spherical particle volume, so it will be becoming pi by 6 into, say, d equivalent cube. Now if I use this d equivalent as parameter to calculate AC, AC is nothing but surface area of volume equivalent sphere. So that will be equal to what is the surface area of sphere? 4 pi d equivalent, sorry, pi d equivalent square. Okay, is this one clear? So that will be my AC. So when we are calculating sphericity, in terms of sphericity, actually we are considering the equivalence of the volume. So initially I told you that we have 4 different variables of a particle. One is volume, second is area, surface area, third is projected area, and fourth is projected perimeter. Okay. So whenever we will be defining the shape factor, we will be utilizing all these 4 variables. We will be using any 2 at a time. So one we will be keeping fixed, and for second we will be considering its equivalence. Okay, for example, when we define the previous factor, then we considered projected area as the equivalent parameter, and now we are considering volume as the equivalent parameter. Okay, and surface area ratio we are actually using to define the sphericity. Is this one clear? Now again the challenge is, for calculating this AC I must know the value of volume. Okay, so then third factor which I can utilize is called as circularity of a particle. So circularity of a particle is given by symbol phi, and it is nothing but equal to PA, perimeter of projected area equivalent sphere divided by projected perimeter of the particle. Okay, so projected area equivalent sphere is once again the first parameter, same. So that's why it is writing it as a pi into dA divided by perimeter of the particle. Is this one clear? So now if you see this parameter phi, still it has some practicality, because projected dA we have seen different methods if we have the projection of the particle, and this perimeter also I can actually calculate even if I have irregular shape. So whatever the graticulate I have placed on the projected area, this grid structure, by taking the help of that, all the covered boundary I can consider as small linear intercepts, and then I can approximate actually to calculate the approximate perimeter of the irregular shape. Is this one clear? So you can see that one simplified thing also to calculate the circularity is that whatever the dA we have calculated using the earlier method. So here what we need to do, again the statistical projected length we need to calculate the way I have explained earlier, and then averaging of that will give me actually dA. Okay, this point is clear. So again to calculate dA I am showing the same thing again. Now because whatever the methods we are studying, actually these are having some sort of complexities involved. Okay, so what we want to do, we want to utilize certain parameters which can be actually easily calculated, so that every time we need not to do so much cumbersome process to calculate these parameters. Okay, so that's why there is slight modification of these parameters, and we are calling these as operational sphericity and circularity. So these were the theoretical fundamental definitions. Now slightly we are deviating from the theoretical fundamental definitions, and we are trying to use some other definitions with the help of which actually we can easily calculate these. Okay, so these definitions are, if I take volume of a particle divided by volume of smallest circumscribing sphere, and then if I take its 1/3 ratio. It's a very easy method. So you have a particle of any arbitrary shape. Within that arbitrary shape, whatever the smallest sphere can be fitted inside the particle. So if I simply take the volume of particle divided by volume of smallest sphere which can be fitted within the particle, and its power as 1/3, that will be giving me the operational sphericity. Is this point clear?
The smallest sphere which covers the particle.
Yes, smallest sphere, yes, which covers the particle.
ये सर अगर कोई कोन की शेप का है थोड़ा सा,
Yes.
तो हो सकता है उसका जो वॉल्यूम है थोड़ा.
So basically, this smallest sphere particle volume will always be greater than your actual particle volume. Okay, is this point clear? If you have, say, this is your actual particle, okay, and what you need to do, you need to fit this particle inside the smallest possible sphere. So this is how you can fill this. Once you are filling this, then you are getting some extra volume at the sides. Okay. Is this one clear? Then we have operational circularity. So operational circularity is projected area of the particle. So if you take the projection of a particle, then whatever is its projected area, this will be a simple area, and area of smallest circle which is actually fitting this particle. So if you take this ratio of 1/2, so these are called as operational sphericity and operational circularity. And then what people have done, people have actually again tried different theoretical analysis and experimental evidences, and they found they are not very good estimates. So if after going through lot of data, then people have once again come in with little bit more modified formulations. So one of the modified formulation is psi w. So this is given the name as working sphericity. It means which is matching well with the experimental data. So that is 12.8 into E1 E2 square cube. So this is a long formula. E1 E2, what are these? We have already seen. Okay. Then for operational circularity, dA by diameter can also be taken as a small another approximation. So this one is area approximation. So instead of calculating the area, simply taking the diameter ratio can also give some workable value. Okay. Then similarly we have one more factor which is called as perimeter equivalent factor. So perimeter equivalent factor is nothing but surface area of the particle divided by surface area of perimeter equivalent sphere. So actual surface area of the particle divided by surface area of equivalent sphere whose projected area is same to that of the particle's projected area. Is this one clear? So that we call as perimeter equivalent factor. So majority of the times you will find utilization of these factors is nothing but as multipliers in order to relate the hydrodynamic forces which are acting on the particles. And these hydrodynamic forces, how we can do? We can estimate the forces, hydrodynamic forces for equivalent sphere, and then that is multiplied with this multiplier. Okay, so there you will see the application of all these factors. Is this one clear? Now, after defining the shape of fluid particles, shape of solid particles, so different factors with the help of which we can actually define the characterize the shape of arbitrary particles. Now we have to go for shapes of the fluid particles. Okay, so one simple rule is that fluid particles will be acquiring the shape which is having static equilibrium in terms of the normal and tangential forces acting at the interface between the two fluids. Okay, so once you have equilibrium of these two forces, there will not be any deformation, any further deformation of the in the shape of the particle. If the forces normal and the tangential forces are not balanced, then you will be finding deformation in the shape of the particle. Is this point clear? So of course, if you have one unbalanced situation, then your shape will continuously evolve till the time new equilibrium is actually established. Okay. So if you consider a simple example, say you have a flat surface, and on this flat surface you have actually placed a liquid of small volume. So this is nothing but a liquid droplet. So typically liquid droplet is of this particular shape. Then other example can be, you have a lighter gaseous phase, and that gaseous phase is actually in a tube. If you consider a air bubble, that will be rising, and in the top if you place some plate, so what will be happening? That bubble will ultimately stick to that plate. Okay, so this is the inverted shape to that of this particular system. So these type of shapes which are formed by the fluid particles when these are actually attaching to the flat plates. These are called as actually sessile shapes. So here I will be calling it as a sessile drop. Here I can call it as a sessile bubble or drop. First you have to understand the difference between the drop or bubble. So if within the entity of the fluid particle I have a liquid phase, then I will be calling it as a drop. If I have a gaseous phase, then I will be calling it as a bubble. Okay. So of course, when a particle is resting on a flat plate, then it has to be a liquid. Then only it will be having more density and it will be resting in the bottom portion. Okay. So it will be a sessile drop. But on contrary, this inverted shape which is rising in the top, one possibility is you have liquid in the surrounding and gas within the fluid particle, so that gas will be rising vertically and sticking to the plate. And second possibility can be you can have two liquids of different density. So one liquid is of heavier density, other liquid is of lighter density. So lighter density liquid will also rise and then stick to the plate. So that's why whenever I am calling this second shape, so within this either there can be liquid or there can be gas. Okay. So if there is gas, then I will be calling it as sessile bubble. If it is a liquid, then I will be calling it as sessile drop. One important point you can notice is in this shape I have actually hatched this portion, and here I am hatching this outside portion. So it means hatched portion over here shows nothing but the fluid of higher density. Okay. So fluid of higher density is actually shown with the dashed lines. Is this one clear? Then we have another shape which is actually kind of hanging from a flat surface. So here you can see if you have a flat surface, and to this flat surface if a liquid drop will be hanging, then what will be its shape? It will be forming some neck like this. Okay. So this is called as pendant drop. And if you have a bubble during the boiling, what happens at the heater surface? There is initially formation of small vapor volume, then that vapor volume grows in size, and whenever its size is growing, its shape becomes something like this. Okay, so it is when it is sticking to a surface, and once it is reaching the sufficiently larger size that buoyancy force is dominating over the surface forces, then this will be breaking from here and it will be lifting off from the surface. Okay, so this particular point I am calling this type of shape is called as pendant drop, and this is called as pendant bubble or pendant drop. If liquid is inside, then I will be calling as a pendant drop. If gas is inside, then a pendant bubble. Okay, is this one clear? Then third possibility can be you have a three-phase system. This is fluid 1, fluid 2 and fluid 3. So three fluids are actually present simultaneously. So here you can see this is fluid 1 of highest density, then another fluid of intermediate density is actually resting over this, and then third fluid is actually in the surrounding which is of lighter density. So here you will be having shape something like this. This is called as floating bubble or drop. So if inside this you have gas, then it will be a bubble. If it is liquid, then it will be drop. Okay. Now all these shapes which I have specified over here, these shapes are nothing but having the balance of, because whenever I am trying to specify these shapes, I am considering that there is no fluid motion. Okay, so all these shapes are corresponding to the rest position of the fluids. So once these are corresponding to the rest positions of the fluid, only two forces will be coming into picture. One will be hydrostatic pressure, okay, and second will be surface tension force. Anything else? Okay, so only two forces will be coming into picture in the rest situation. One will be hydrostatic pressure because of the gravity, and second will be surface tension. So all these shapes can be specified by the balance of hydrostatic force and the surface tension force. So here you can see this rho p minus rho gy, it represents nothing but hydrostatic pressure. Okay, and then when we are having these shapes, then these shapes are having certain curvature also. So because of the curvature also there will be some pressure. Okay, what do we say that pressure? So if you have a simple drop, there is higher pressure within the drop, this inner pressure, and this is outer pressure. What is the difference of inner pressure minus outer pressure? 2 sigma by r naught. If r naught is radius of this, 2 sigma by r naught. Okay, so it means that if you have a curved profile, then there will be change of pressure because of the surface tension also. Okay, so this first factor 2 sigma by r naught is nothing but the pressure because of the shape of that particular curvature of that particular interface. Okay, so this is called as Laplace pressure. Have you studied fluid mechanics? So this is called as Laplace pressure. Okay. Then, so it means that if you consider that you have fixed a y coordinate over here, this is the origin of y and this is increasing in upward direction. Okay. So this is the reference point for y. Now you can see that at this point there will be some curve. There is some curve. Okay. So radius of curvature of this particular curve is actually nothing but r naught. Okay. All are clear with this idea? Now, if I take any point other than this location, so when I will be moving away from this point, then what is happening? There will be change of curvature. Okay, so that change of curvature is actually given by this formula. How we calculate curvature at any arbitrary shape? Say if you have any arbitrary shape, this is any arbitrary shape, how to calculate curvature at this point? Say if you have to calculate curvature at this point. So how mathematically you can calculate curvature? First you need to draw a plane which is normal to this, and in that particular plane you have to draw some curve which is tangent to this. So whatever the radius of this curve will be coming, that will be nothing but your r1. Is this point clear? Then what you need to do, after that you need to draw another plane which is perpendicular to this first plane, and about this plane whatever the radius is there, that is what our r2 radius. Okay, so 1 by r1 is curvature in one plane, 1 by r2 is curvature in other plane, and sum of these two is nothing but called as our mean curvature at that point. Is this one clear? So if you have any arbitrary shape, what you need to do? First you need to draw a normal to that, and then you have to consider that you have to make a plane which is parallel to that normal, which is parallel to the normal and intersecting at that point. And in that plane, whatever the curve you can fit through that particular body, that will be giving you one principal radius of curvature. Then what you need to do? You need to do another plane which is perpendicular to that particular one. And for example, if I take the example of a sphere, so now can you tell me for a sphere how I can find, how I can calculate for a sphere? Say this is my sphere. This is nothing but a sphere. Now how I can calculate? Say at this point I want to find curvature. What I will do? I will first draw a normal to this. This is my outward normal, and parallel to this outward normal now I have to draw a plane. So parallel to this outward normal, if I draw a plane like this, and if I view the top view of this plane, then this is my plane, and on this plane projection of this sphere will be nothing but a circle. So it means I will be getting one radius as radius of this circle, okay, which is identical to radius of the sphere. On contrary, now what I need to do, one plane is like this, other plane I need to consider in such a way so that it is again intersecting with the normal and perpendicular to the first plane. Okay, so it should intersect with normal and perpendicular to first plane. So my plane will be something like this. If you consider like this, then this plane is intersecting with the normal also, and it is perpendicular to the this previous plane also. So now in this plane, if you take the projection of the sphere, again it will be a circle. So that will be nothing but your R. Now if you have to calculate the mean curvature, that will be nothing but 1 by R1 plus 1 by R2. For sphere, R1 will be equal to R2. So if R1 is equal to R2, then you will get 2 by R as your mean curvature. And what is surface tension force or surface tension Laplacian pressure? Is nothing but sigma times mean curvature. So mean curvature is 2 by R. So 2 sigma by. Okay, so that is for a perfect sphere. Okay, so what I am saying is this 2 sigma by R naught is corresponding to point O, radius of curvature at this point. Because at this point, with reference to this point, I am calculating the hydrostatic pressure. So at this point, if I have my complete curve which is following this sphere, then only I will be having these two balance to each other. Okay, like in case of spherical bubbles and spherical drops. But when a sessile drop is resting on the surface, its shape is not a perfect sphere. Okay, so it is having actually shape other than the sphere. So if I take any other point, say at this location, so at this location what you will be finding? It is having some other larger radius of curvature. Is this point clear? It is having some small or large? Will it be small or will it be large? It will be small. You have to see to that. Yes? Yes, it will be case wise. But one simple thing you can see, how you can estimate whether this has to be small or large, that let me tell you. You are at this point, okay? And with reference to this point, you are calculating y. Once you are going to this point, value of y is becoming less. If value of y is becoming negative, because at this point value of y is 0, and below this any point value of y will be negative. Once your value of y is becoming negative, this left hand side will become negative, because particle is a drop, its density is larger in comparison to density of the surrounding phase. So that's why rho p minus rho is a positive quantity. So this y is becoming negative. So that's why this left hand side is negative. Now this first part of the right hand side is positive and this second part is negative. So this negative portion has to be larger than the positive portion. Then only this will be becoming equal to the left hand side, which is a negative quantity. So in order to dominate this negative portion, the value of R1 and R2 should be small. Then only this will be large. So it means that in case of your sessile bubble or drop, if you move away from the center location along the curvature, then your radius of curvature actually decreases.
सर ये जो इक्वेशन है वो हर पॉइंट पे वैलिड है
Yes.
तो सर आर नॉट फिक्स्ड है
Yes.
जो टॉप को
Yes, because R naught is corresponding to the reference of y at which hydrostatic pressure is actually balanced.
सर ये लेस होगा तभी तो बबल बनेगा। इसका मतलब ये भी बोल सकते हैं कि अगर ये लेस होगा तभी बबल बनेगा।
This shape will be possible then. Okay, so Achman, you can consider it like this. When you have a sphere, okay, so in case of a spherical bubble, inner pressure and outer pressure are different, and inner pressure and outer pressure are actually equated through this surface pressure gradient, which is 2 sigma by R naught. Okay, so this is balancing the inner pressure and the outer pressure. Now, for a perfect spherical shape, the point at which you are calculating this hydrostatic pressure, that is balancing to this point. Okay, once you will be moving in any other direction along the, with reference to the balance point, then what will happen? Your hydrostatic pressure will change. So corresponding to the new point now, whatever the change in hydrostatic pressure you are reporting, that is corresponding to the first reference position. So first reference position is actually balanced by 2 by R naught. So this 2 by R naught will always remain the same here. One thing can happen, if in place of this you take this as your reference point for y, then your R naught will be nothing but radius at this particular.
so any point that we choose
Yes, but why we are over here choosing point at the center? Because this is nothing but a axisymmetric shape. So axisymmetric shape at the central axis will be having both the radius same in first plane also, in second plane also. So that's why this radius I am simply writing as 2 by R naught. Is this point clear now? So his question was that why this 2 by R naught should remain always fixed. Okay, so basically this 2 by R naught is coming to the point with reference to which we are balancing our hydrostatic pressure. Okay, and so if I take this balance point to any other location, then that particular quantity will be fixed. But if I shift my location from this point to any other location, then my R1 and R2 will not be always same. R1 and R2 will be only same at the point where I am having axis of symmetry. Okay, so that's why I am
the calculation easy करने के लिए
calculation, yes, to make the calculation easy, reference point we are considering at the axis of symmetry, because at the axis of symmetry my value of R1 and R2 at that particular point will be same, which will be equal to R naught. That's why I am writing it simply as 2 by R naught. All are clear with this or not? So you have to do two things: visualization and basic understanding of the fluid mechanics. If that is not there, then you will not be able to understand this equation. Is this one clear? Or do I explain this again? So then we have other shape. So you can see the pendant shape over here. So my reference point is here at the bottom point. Now in this case, at this point my radius is R naught. So rho p minus rho into gy is equal to sigma times 2 by R naught is balanced at this point. But when I go away from this point, so say I am at this location. So at this location now what will be happening? There will be new radius of curvature and my y will also be positive. So if I am having y value as positive, this value will be becoming positive. So this value 2 by r naught into sigma should dominate. So in order to dominate this value, the value of r1 and r2 should be large. So in case of pendant drop, when I move away from the axis of symmetry along the surface of the drop, my radius of curvature actually increases. Is this point clear? All are clear with this idea?
सर एक चीज सर जिस पॉइंट पे R1 और R2 इक्वल है सर उसी पॉइंट पे तो ये इक्वेशन सेटिस्फाई होगी अगर हम रेफरेंस पॉइंट उसको मानते हैं बिकॉज़ उसमें y 0 होगा
Yes.
और ये साइड भी 0 होगा
ये side be 0. Because at that point R1 and R2 will be exactly equal to,
तो सर मतलब फिर हम रेफरेंस पॉइंट कहीं और नहीं ले सकते ना
yes, yes. No, reference point we can take at other point also, but then I will not be using 2 by R naught in the first term. Then in place of 2 by R naught, there also I have to use 1 by some RF1 and RF2. Understood?
Yes.
So corresponding to that reference point, RF1 will be equal to R1, RF2 will be equal to R2. Clear? Okay. So all are clear with this equation? Shall we move further? Okay. I think let's stop at this point, then we will discuss further. And in the meantime, please revisit your concepts of basic fluid mechanics.